Okay, I'll now talk about modern offline RL algorithms. So as Sergey discussed, action distribution shift is one of the biggest issues in offline RL methods. In particular, when we use an actor-critic method, the target queue network gets queried on actions A prime sampled from the current policy, and these actions A prime can be out of distribution or unseen actions. When we query the target network on these actions and utilize the resulting value for the backup, we are essentially backing up erroneous values that we are never really correcting during training because we train on the distribution defined by the behavior policy. So how can we fix this issue? So to fix this issue, what we can do is we can add a simple fix here, which is in addition to training the policy to maximize the expected Q value, we make sure that the learned policy pi theta in this case is close to the behavior policy pi beta. And this closeness constraint can be expressed in many ways, and we'll discuss some of these in this tutorial. And to call this a class of methods generally, we use the name policy constraint because what these methods are doing is essentially constraining the policy using some divergence metric to be close to the behavior policy. To get some intuition for why something like this can help fix the action distribution shift problem, let's visualize the Q function landscape for a given state S across the action dimension. And let the dashed red line denote the behavior policy in this case, and the blue line denotes the manifold of the Q function. Now, when the Q function, when we don't apply any such correction, we'll end up using the erroneously high Q values at unseen or out of distribution actions for the backup, as shown in the plot. However, when we actually use an action, or when we use a policy constraint, what we are really doing is that we are making sure that the actions A prime that we are using for the target, using for the backup, are drawn from regions that are sort of close to the distribution of the behavior policy. So they are close to this dashed red curve on the slide. And what this makes sure is that it limits the amount of out of distribution actions that are used for training the Q function. And the actions that are used for training are also the actions that we train actually. So the actions that on which we train the Q function are also the actions that are used to generate the target labels for training the Q function. So in a sense, what it does is that it prevents the action distribution shift from problem in offline RL. So what are the different classes of policy constraint methods that we could use? So this divergence D is pretty much left open to us. So what are different ways in which we could instantiate this? So I would partition the class of methods into two broad classes. The first class of methods, I would call them distribution constraint methods. So what these methods do is that they essentially pick this divergence D to be some sort of a probabilistic distance between pi theta and pi beta. For instance, you could choose it to be the KL divergence. You could choose it to be a more general F divergence. And many other distances that are basically probabilistic notion of distances between two distributions. When we use such a distribution constraint, what we typically find is that the resulting policy, which is shown in purple on this diagram, is in a sense close to the behavior policy in terms of its densities. So the density of pi theta of a given S is in a sense close to the density of pi beta of a given S, as you see on this plot. What we could also do in here is we could also solve for the distribution constraint in a sense implicitly. So the current methods that I just discussed, what they would do is they would express this constraint and they would solve this constraint optimization problem for the policy using some technique. For example, in practice, you could use Lagrangian dual descent. However, another class of methods, what it does is that it would solve this constraint optimization problem in closed form and directly implement the solution of that closed form problem in the code. So to do that, what you can do is you can solve for this problem, which asks you to maximize the Q value and also minimize the divergence, which is, let's say, the KL divergence in this case. You can solve this in closed form, for instance, for the KL divergence, and you'll find that the resulting solution pi theta would be proportional to the behavior policy density pi beta of a given S multiplied by the exponentiated Q value divided by alpha. And you can implement this directly in code. And I would call these implicit distribution constraint methods, and they've also been explored a lot in literature so far. So to sum up, basically, there are many other forms of distribution constraint methods in this case, and they each have different benefits over each other. For example, in some cases, optimization might be easier. In some cases, you can represent the constraint easily. In some cases, you can solve them in closed form, etc. And it really depends on case-to-case basis as to what you would want to use in a practical scenario. Okay, so the next class of policy constraint methods are support constraint methods. Support constraint methods aim to constrain the learned policy pi theta to the support of the behavior policy. The support of the behavior policy is the set of all possible actions that are highly likely under the behavior policy. For instance, the set of actions that you see between the vertical dashed lines here on the slide. And the intuition behind these methods is that what you really want to constrain is you really want to make sure that the learned policy pi theta samples only those actions that are within the support of the behavior policy, or samples only those actions that are highly likely to be also sampled by the behavior policy. And you don't really want to compare the density ratios of pi theta and pi beta, which is what the distribution constraint methods did. So one way of implementing such support constraint methods is to, for instance, take the maximum mean discrepancy distance between the learned policy pi theta and the behavior policy pi beta, and estimate this using only a few action samples. And if you do that, you can approximately argue that you are doing some sort of a support constraint or a support matching style divergence. Now, what does the support constraint do? So a support constraint can, in principle, find one of these yellow policies if the behavior policy is given by this dashed red line that you see on this Q function landscape for a given state here. We can also generalize support constraints to use other sort of distances. For example, you can use these general class of metrics called integral probability metrics. And what do they do? They basically they choose a function class, calligraphic f. And what they'll do now is they'll compute the expected function value for all possible functions in this function class under the distribution pi theta and under the distribution pi beta, compute the difference, compute the absolute difference, and take the maximum possible difference value here. Now, in principle, if you have infinite samples, these metrics would also be zero when pi theta is exactly equal to pi beta. But otherwise, you see, when you implement this using finite samples, you're sort of getting a behavior where you are not really comparing the densities of pi theta and pi beta, but you're only looking at sort of the expected function value on samples from them. So they have a sort of a support matching style flavor as well. You can also do something different. For instance, one of the papers called SPIB, what it does is that it constrains the learned policy pi theta to take exactly that density value that the behavior policy takes. So pi theta of a given s should be equal to pi beta of a given s on actions that are out of support. And for all other actions that are within the support, you're free to choose whatever density you want. And that also has a similar flavor where you are comparing sets rather than the density ratios. Now, when you are operating in discrete action spaces, you can also do many other sort of constraints. For instance, one of the choices of constraints here that you can do is you can take all the action samples that you saw for a given state S. So I'll call that the support of the action distribution at state S. And for all other actions that you didn't see, you penalize the total amount of probability mass your learned policy pi theta is putting on those actions. So a distance that looks like what you see on the slide, the sum of pi theta of a given s over actions not drawn from the support of the data distribution at state S. You can also do something different. For instance, when let's say you're doing Q-learning where you're using a max over a prime backup. Now, instead of doing a max over a prime of qs prime a prime, you can restrict the support of actions you compute a max over. And that's also a valid support constraint method in this case. So there are many ways of doing support constraints. Now, some of these discrete action methods may not be very easily generalizable to a continuous action space, or they might end up being a bit biased, but there are many possible ways you can do them overall. Okay, so far we have discussed these two broad classes of methods which involve distribution constraints or support constraints. But how do these methods perform in practice, or do they even differ in practice, or why would we expect them to be different in practice? So to answer this question, let's first of all take a step back and look at what do policy constraint methods do in the first place. So policy constraint methods, they end up changing the objective that the policy is optimizing. So you're no more solving the standard RL objective, but you're also penalized for deviating too far away from the behavior policy. So in that sense, you have a conservative, you have a term that encourages more conservative behavior for the policy that you're learning. So certainly, the different constraints or different choices of D in here will alter the behavior of the algorithm because now different choices of D will give us very different policies that may or may not optimize the standard RL objective very well. So how does this? How do support versus distribution constraints play out? Meaning that are support constraints necessarily better? Are distribution constraints necessarily better? Is there a way to compare the two, or what happens in that case? So going back to the figure that we have been looking at so far, turns out that distribution constraints or distribution matching will make you choose policies, or make you choose one of those purple policies that are in a sense close to the behavior distribution in terms of a density sense. So you would want pi theta of a given s to be close to pi beta of a given s in terms of a density sense. Whereas a support constraint would make you choose one of those yellow policies that is not close to the behavior policy in terms of a density sense, but it chooses actions for which the behavior policy density is large enough. Now, imagine a scenario where we have a uniform behavior policy. So the behavior policy that is in our offline RL problem takes each action uniformly. In that case, what we'll end up finding is that the distribution constraint option in here would end up training a policy pi theta that has to pick each action with some or the other probability. Whereas the support constraint version would end up giving you a policy that can exactly pick the optimal action with 100% probability and put zero mass on everything else. And that policy is going to be more optimal because it exactly chooses the one action that we care about that maximizes return, whereas the distribution matching one may not be optimal because it has to match the distribution too, and so it has to be close to sort of a uniform distribution over actions in some way. And so in theory, at least, support constraints can be better. And you can also formalize this intuition on many sort of simple examples like this 1D line word example where only a support constraint can give you a policy that can take you from a starting location to a goal location. And as soon as you use distribution constraints, you will find that there's negligible likelihood as a function of how many steps you need to take to reach the goal from the starting state. There's exponentially lower likelihood if you do distribution matching that you will reach the goal location, depending upon how long this trajectory is. Okay, so there are also other variants of policy constraint methods. So far we discussed distribution constraints and support constraints. There are also different variants. For example, you can have a variant that does not utilize or does not penalize the policy distribution pi of A given S. So far all the methods that we discussed, they talk about some property of pi of A given S or pi theta of A given S and compare that to some property of pi beta of A given S. But we can also do something else. For instance, we could directly define a constraint on the state action marginal distribution of the policy. So we could define d over pi theta comma pi beta as the KL divergence between d pi of SA, which is the marginal state action distribution under pi, and d pi beta of SA, which is the marginal state action distribution under the behavior policy. And such a thing can also be technically viewed as a policy constraint in this case. There's a lot of work on this actually in some of the more recent days, and the family of dice methods is based on this. And a lot of this work has been done primarily in the off-policy evaluation literature, but it can also be used for offline RL, as some of these works also do. I'll not go into too much details about it, but I'll briefly mention one point here, that these marginals are sort of not easy to compute in an offline scenario, because pi of A given S is generally a model that you model, but d pi is not computable unless you exactly know unless you exactly unroll the policy in the environment and compute the distribution over state action pairs. So computing d pi itself in an offline scenario can be very hard. And what some of the methods typically do is that they try to then estimate the density ratio. So they estimate d pi of SA divided by d pi beta of SA. And they implicitly use this for an RL, for RL with a modified objective. And as Sergey sort of discussed previously, you can write down a Bellman equation, a Bellman-like equation over the weights W of SA and then solve for them. But I'll not go into it in too much detail. And if you're interested, a lot of these details can be found in the references that I listed on this slide. Okay, so finally, how do policy constraint methods perform in practice? So we have seen a number of these methods. How would they perform when we run them with a deep neural network and on a practical task? So in order to understand that, let's start with a brief introduction to the problem setup. So in this case, we'll be comparing a bunch of methods, and the problem would be to optimize reward. But the data set that is given to us, the offline data set, it consists of data generated from a random policy, so a policy that takes all actions uniformly at random, and a policy that is partly trained. So it's a policy that you obtain by training a standard online agent partly. So you train it for a few steps. That the policy that you get, it's called a mediocre policy or an intermediate policy. We freeze that policy, collect a bunch of data from it, and use that as our data set. So we take a mixture of data from each of these random and mediocre policies, combine them, and that's the replay buffer or the data set provided to our agent. In this case, for example, on these Hopper and Walker domains, we'll see how these methods perform. And before going into how these methods perform, let's first of all look at what are the baselines we'll be talking about. So we'll talk about a naive off-policy RL baseline, which is soft actor critic. We'll talk about behavior cloning, which is standard supervised learning imitation. And we'll have three policy constraint methods, out of which Bear, which is the one shown in red, is a support constraint method, and BCQ and BRAC are distribution constraint methods. Now, first of all, as a first insight, note that all the three offline RL methods, or all the three policy constraint methods, are actually better than behavior cloning, which is shown in yellow. So that does indicate that offline RL can do much better than just vanilla cloning or behavior or supervised learning on the data set. And that's a good thing, because that just shows offline RL is really a promising thing to be doing, the promising thing that we should be doing. The second thing that you should note is that different choices of D do matter. For example, there's a clear difference between BCQ, BEAR, and BRAC in both of these plots. And there's a clear difference. It's not just sort of randomness in this case. However, one more thing to note here is that BEAR, which is a support constraint method, is not the most optimal in either of the environments. So the most optimal is the BRAC method, which uses a distribution constraint at the end of the day. So all of the discussions we've had about support versus distribution constraints, they actually hold true in practice. They actually hold true in theory, but there might be some differences in the expected behavior on a practical task, because there might be some other factors at play that we haven't really analyzed, or that we even don't know so far. So there's a discrepancy between what we expect and what we obtain in practice, and that's an important research question then as to why this is the case, and what does an investigation of this reveal reveal for future algorithmic development. However, we might ask ourselves if policy constraint methods are sufficient now. But turns out that if we run these policy constraint methods, BEAR and BRAC, for example, on a harder task, which is an ant maze navigation task, where you're going to be training an ant robot to navigate from a start location to a goal location from an offline dataset, and the offline dataset does not consist of even a single trajectory that takes you from the desired start location to the desired goal location, and you actually need to stitch together parts of trajectories to get that behavior. In such a scenario, which is sort of a complex offline RL task, we do find that most of these methods, they do not perform very well. So as soon as you increase the complexity of the maze, for example, for the medium and the large maze, which you see here, none of these policy constraint methods perform any non-trivial behavior in this scenario. And so what this tells us is that there is sort of work to do, and it's not that policy constraint methods are the answer to everything. Okay, so then where do we go next? As in, we realize policy constraint methods are not super good, but then what is good, or what kind of things should we think about for algorithmic development? So to understand that, let's look back at what are some shortcomings of policy constraint methods. So first of all, policy constraint methods typically require estimating the behavior policy. What that means is, when we apply such a constraint on, or when we apply this policy constraint on a policy improvement step, the policy pi beta is typically estimated from the dataset. So it's not, pi beta is not given to us, as in we don't know what pi beta of a given s is, but we estimate pi beta from our static dataset. And if we estimate this behavior policy wrongly, for example, if we fit a unimodal policy to a multimodal distribution, we might end up getting a constraint that does not meaningfully constrain pi theta to the regions that are truly in distribution, because our behavior policy, our ground truth estimate of what the distribution of the data is in particular wrong. And this is one of the reasons why, for example, in the ant maze scenario, things are not that great. Another reason for why policy constraint methods are not that good is because these methods often tend to be too conservative. What I mean by that is, for instance, if you know, or if you can somehow figure out during learning that at a particular state, all the actions are equally bad or equally good. For example, if all actions have zero long-term reward, then we do not really care about constraining the policy there, because we know that if we take any of these actions at that state, we'll end up getting the same reward. But a policy constraint method would actually still impose a constraint that requires pi theta to be close to pi beta at that state. And when we utilize function approximation, we might end up sort of affecting the policy performance at other states as a result of this, and which might not be good. And so these methods, they tend to be too conservative. They tend to be too close to the behavior policy in such scenarios. So we ask ourselves if we can do better in this case, and we'll discuss that next. Okay, to understand how we can do better than policy constraint methods in offline RL, let's revisit the motivating example that we started off with. So this was the example of running a naive off-policy RL method on an offline RL task where the dataset came from an expert policy. In this case, it was clear that the Q values were drastically overestimated. and the Q values ended up overestimating unseen outcomes that were also bad outcomes, and so they ended up performing very poorly. Now, policy constraint methods, they aim to solve this issue by making sure that the resulting policy, that the learned policy, is close to the behavior policy in some way or the other. So they were making sure that the actions taken by the resulting policy are not too different from the behavior distribution, and hence, by proxy of that, they could have solved this issue. But now I would argue that policy constraint methods actually end up overdoing it, in the sense that we don't really need to constrain the action distributions of policies if for certain outcomes, the algorithm does actually know that those outcomes are bad. So even if we have not seen a certain outcome, but the algorithm somehow generalizes, or my Q function somehow generalizes to in a way that the Q value for an unseen behavior is super low, I don't really need to constrain the policy separately on that outcome as well. So can we directly sort of tackle the overestimation issue in this case, which is sort of a more primary cause for concern here, rather than constraining the action distributions, which is certainly a valid way to solve it, but not the most optimal way to solve it. And in this section, what we'll do is we'll discuss these methods, and we'll call them conservative methods because they would try to solve this overestimation issue by, in a way, learning a lower bound on the policy performance in multiple different ways. And we'll discuss two of these methods. One of the classes of these methods would be model-based methods, and the other class of methods would be model-free methods in this scenario. Okay, so let's get started with conservative model-based offline RL methods. So before going down into what exactly how exactly we would get conservatism in the model-based RL framework, let's first discuss what kind of a model-based RL framework we could use when we have an offline dataset. So let's imagine we have a dataset of transitions. What we'll do now is we'll train a dynamics model or a neural net dynamics model from this dataset, which would aim to map state action pair st, at to the next state st plus 1 that we would get from it if we were to execute action at state st. It would also learn a reward function that would predict the reward value I would have gotten in the actual environment if I were to execute action at state st. And now what I'll do is I'll treat this resulting or this learned model and the learned reward function as sort of a proxy world that I could essentially do model-based RL or model-based planning in. So I'll treat this as the dynamics, as if it were the true dynamics and the true reward function. I'll run RL or planning on it. Now, as we would expect, even planning or policy optimization under the learned model will lead to unseen outcomes because the learned model and the learned reward function will not be accurate. They'll be inaccurate, especially if the data distribution is not high coverage. And planning under them would make the policy choose those actions that would take you outside the data manifold towards unseen outcomes. Now, we can solve this issue in multiple ways. For example, one option is the option that we saw just before, which is the policy constraint methods. However, as we discussed, we not want to just directly apply them because these methods they tend to be overly conservative. So what else can we do? So one of the options that has been explored in literature is to make the learned reward function be conservative. So what these methods do is that they would make the learned reward function be in some sense account for outer distribution-ness or unseen outcomes, and they would just simply run model-based RL on this modified reward function that you train. To more schematically indicate this, let's imagine that this parallelogram was the possible space of all state action pairs in an MDP, and the green colored region is the region that was actually observed in my dataset. And what I'll do is I'll keep sort of the unaltered reward function that I could learn on this green region, but for the region outside of it, I'll just make the reward function be more conservative, and I'll just run model-based RL on this new modified MDP. So how can we get such conservative reward functions in offline RL? So I'll discuss two works in here, which are two recent works, which are cited on the bottom of the slide. And both of these works take this approach of modifying the reward function using an additive transformation. So they would take the original reward function and subtract a sort of an uncertainty metric from this original reward function to obtain the modified reward function. So U of SA is a notion of uncertainty that dictates whether a state action pair is in distribution or is out of distribution, or is whether the state action pair is seen or unseen. And we subtract some quantity based on that from the reward function. So how can we first of all estimate uncertainty in a model-based offline RL scenario? So we leave aside the kind of exact function that we would subtract from there, but how can we even get some notion of uncertainty in the first place in such a scenario? So one of the common ways to figure out uncertainty is to train an ensemble of models on the given dataset. So what we'll do is we'll take the dataset, we'll either partition that into different disjoint subsets, or we'll just take the entire dataset or we might want to add noise, etc. There are many ways to do it. And what we'll do is we'll train multiple dynamics models, an ensemble of dynamics models on this data set. And what we'll do is we'll check agreement in their predictions to figure out whether a particular state action pair is in distribution or out of distribution. And why would we do this? So to gain intuition for why something like this is meaningful, let's look at sort of a curve that we can obtain by fitting an ensemble of models on a simple 1D regression task. So the curve that you see here is a simple 1D regression task. The solid line that you see is the ground truth function, and the various bands you see are sort of uncertainty, or they can be regarded as sort of the predictions of an ensemble of models that was trained on the data, where the data consists of these red colored dots that you see marked on this curve. So you're seeing data only coming from these red colored dots. You're fitting an ensemble of models. Now the predictions at the observed points will be accurate, because each of the models in the ensemble would end up predicting those values correctly. But for all other points that were not seen, different models will make different mistakes on those unseen points. So they'll not mistake in the same way. They'll make mistakes in different ways on unseen points, and therefore you'll find that the variance of predictions on these unseen data points will end up being super high. So if I do actually end up checking agreement of the models in my ensemble, I find that the agreement would be higher on seen points or in distribution points, but it will be lower on points that are out of distribution or unseen. And so I can use this agreement notion to figure out some concrete metric for U of SA that we'll discuss next. So what do these model-based offline algorithms choose as the uncertainty metric? So the first option, as we discussed in the previous slide, is model disagreement. That is, we train a bunch of dynamics models, which is indicated by Pi and Pj. We compute their mutual disagreement. For example, we can take their predictions and compute some sort of L1 or L2 distance between the resulting states that are predicted from these models. And what we can do next is we can make this function U of SA be the maximum possible reward, meaning that we'll subtract the maximum possible reward from the reward function R of SA if the maximum disagreement over the models in the ensemble is more than some threshold. So we specify some hand-chosen threshold. We'll compute the disagreement mutually. If that is super high, we would subtract, we'll make the reward function be too small by subtracting the maximum possible reward we could have obtained over any transition in that MDP. And this is the idea behind Kidambi et al. 2020. That is one of the ways which does this. Another way we could do this is to take into account some notion of prediction uncertainty, where let's assume for now where we instantiated dynamics models or the ensemble of dynamics models as multivariate Gaussian distributions. And what we can do here is we can make the uncertainty not be more like a discrete function or a step function, but more like a continuous function which corresponds to the maximum possible Frobenius norm of the covariance matrix of the model predictions over the ensemble. So it's the maximum over all possible ensemble elements, the Frobenius norm of the sigma or the covariance matrix of the prediction at a given SA input pair. And this is the idea behind MOPO, which is U et al. 2020. Now, we can use these kinds of metrics or even new metrics that we can potentially develop, but how can we then do RL with it? Or how do we use this for model-based RL then? So we've obtained a reward function, and now what we can do is we can either do more like a Dyna-style algorithm where we'll generate more data from our resulting learned model and the learned reward function, and the reward function is also modified now to be more conservative. And we simply then run a simple model-free off-policy RL algorithm on top of this data. That is one approach. The other approach is to now do trajectory optimization or planning under the resulting model and with the new reward function. That's also a potentially viable approach. And both of these have been explored in literature, and their trade-offs can be looked upon in the references on the slide. So if you've noted, the common theme so far has been to make the reward function be more conservative. But in principle, we could also make the dynamics be different, because so far what we've been doing is we've been learning the dynamics directly from the data. It's certainly an ensemble of dynamics models, but we haven't really modified the elements in the ensemble. They're just trying to match our data set or match the dynamics in the data set. In principle, we can also alter the dynamics in some way and then run model-based RL on it. But both of these methods discussed so far do not do that. So a potentially open question here is whether we should actually modify the dynamics or not, or is reward whether making the reward be more conservative is sufficient or not in such offline RL scenarios. So how does model-based offline RL method, how do such methods actually perform? So the first thing which I would want you to look at is that naive model-based algorithms can also help with some auxiliary challenges that we find in offline RL. So as Sergey discussed, sampling error and function approximation error, these are challenges which are there in RL methods in general, but they get exacerbated when we do offline RL because we cannot really correct errors by doing more on policy or online data collection. Now, naive model-based RL methods can help a lot with some of these issues like sampling error, even if we don't really correct for distribution shift. So in cases where the distribution shift issue is not too large, even there you will see that the difference between MBPO, which is a model-based method, and SAC, which is an off-policy RL method, there's a huge difference between their performance on these plots. So that's a good point here, which is in favor of model-based methods. Secondly, I would discuss some results from this table, which I took from the MOPO paper, where the first thing I would ask you to look at is that conservatism does really help with model-based RL methods, especially on narrow data sets. So if my distribution of state action pairs that I see in my data set is not too broad, I actually do find that conservatism or being conservative or modifying the reward function to be conservative does actually help. For example, if you look at the rows indexed by the word medium on these in this table, you'll find that MOPO, which is the conservative variant of MBPO, is actually much better than MBPO itself. Moreover, you'll find that these model-based methods, they tend to be much better than policy-constrained methods. And they especially are better in cases where they end up being less conservative. So for example, on the rows marked by the word mixed, you'll find that in all the three domains, the model-based variant, which is MOPO, is much better than PAIR or BRAC, which are the corresponding policy-constrained methods. And this is because of the reason that we discussed, that policy-constrained methods can be too conservative, even though you don't need that much conservatism in the first place. Okay, we'll now talk about value function regularization methods for offline RL. So far, we looked at handling overestimation by penalizing the reward function. For instance, using an uncertainty metric computed using an ensemble of learned dynamics models. However, in a model-free setting, we do not really have access to these learned dynamics models, and so we need to come up with a way to directly penalize the learned Q function or the learned value function. So one of the approaches for doing so is to add a penalty which is based on a policy constraint to the value function training. For example, we could compute a notion of divergence D between the learned policy pi theta and the behavior policy pi beta and subtract that from the Q function training. These kinds of approaches have been extensively studied under the name KL control in the standard online RL setting, as well as more recently in the offline RL setting. And these works in offline RL that implement such an update do actually show empirically that a value penalty version does perform much better than the corresponding purely policy constraint counterpart. Now, that is actually promising, but then these methods also still utilize a policy constraint, although in a different form than a policy constraint method. But still, this notion of divergence is something that we wanted to get rid of because we thought this was getting too conservative. So one of the other classes of approaches that you can do here, they can actually get rid of this divergence by directly changing the objective for the Q function training to make a conservative behavior automatically kick in. So you need not require this notion of divergence, but you directly change the objective for training the Q function. One way to do so is to train the Q function using this objective that you see on the slide, where in addition to the standard TD error term, you have an additional regularizer that minimizes the big Q values at each state in the dataset. So what this regularizer does is that it picks out actions for which my Q function has high values, and it minimizes or pulls those Q values down. Now, why can something like this actually work? So in this case, if you see here, the TD error objective is going to push up the Q values at state action pairs that you have seen in the dataset because you are doing Bellman backups at those states. Whereas the regularizer term is going to pull down the Q values which are high on outcomes that you haven't seen, or on outcomes or on those actions which you haven't seen in your dataset. If the Q values of those actions are high, you're going to pull them down. So in this case, you're making sure that the unseen outcomes are never overestimated because their Q values are just sort of minimized a lot. So we formalize this idea and we call this conservative Q learning, where what you do is you first of all learn a conservative Q function using this update. And you can even formally show that for all states in the dataset and for all actions at those states, the learned conservative Q function is going to be a lower bound on the true Q function of the policy. And because of this reason, it's no more going to be overestimated, and hence you can directly apply a standard actor critic algorithm, but with this conservative Q function for training the policy. So you learn this conservative Q function and then optimize the policy using a standard actor update in a naive off policy RL algorithm But instead of using a naive Q function, you will use this conservative Q function for that update. Now, why this is good, because it avoids overestimation, it can still be too conservative, because here there's no constraint on how low the Q values can go if you train with this objective, because you're essentially just literally minimizing the Q values and trading that off with the TD error term. So we can instead come up with a slightly different version of this algorithm, which is called CQL-V2. And what it does different from V1 is that in addition to the terms that V1 has, which means it's still minimizing the big Q values, it's still minimizing the standard TD error. In addition to that, it's also maximizing the expected Q values on the dataset, or the expected Q values under the behavior policy. And what this gives us is that it no more guarantees us that the Q function or the conservative Q function will be a lower bound pointwise on the true Q function. So in that sense, it can actually be an upper bound, or it can actually overestimate the Q values on state action pairs, which I actually see in my dataset. But still, the value function of the learned policy under this conservative Q function is going to be a lower bound on the true value of the policy. And so in that sense, it is much tighter, because it's no more underestimating the Q function completely, but it's still underestimating the right bits, meaning that it's still underestimating the value function or the policy value, which is what we care about in RL. I would also like to bring a related connection here, which is that these works from 2014 and 2017, they have a similar objective in a setting where they want to, first of all, where they want to do Q learning along with demonstrations. But their particular loss form that they utilize is a little bit different, because they utilize some sort of a margin loss between the big Q values and the data Q values, rather than just having a linear loss like what we have here. Also note that the conservative Q learning V2 update has a saddle point problem where you're minimizing the Q function and you're maximizing mu, which can be pretty unstable to solve in practice because you have these two neural networks then which need to compete with each other. So a different way to implement this in practice is to instead solve a soft optimization problem, where you now have a soft max of the Q values at a particular state, and you are going to be minimizing that. You are going to be maximizing the Q values in the dataset, so the expected Q value in the data, and also you're going to be minimizing the TD error that we had. So the max over mu goes away, and you now have a soft max over Q functions here. And the algorithm, as we discussed, you're still going to be training the Q function using this objective, and the policy is still trying to maximize the expected Q value or the discounted return, as you see here. Now, before discussing how these methods perform in practice, let's talk a bit about how this value regularization that we discussed here, where you are changing the objective for training the Q function, how that is actually different from a policy constraint penalty, which is the way one or the approach one that we discussed. So policy constraint penalty, as you see here, it subtracts some sort of a penalty from the backup. In a tabular setting, you can even show that a value regularization approach, like CQL that we discussed today, even that subtracts a penalty from the Q function backup. Now the penalty is a bit different. It's not a standard KL divergence penalty or something, but it's still like a penalty between pi theta and pi beta. But in the function approximator setting, the policy constraint penalty methods would end up projecting down the entire modified target Q value, where you compute the target Q value as the reward function plus gamma times the Q value of the next state and next action, subtract the divergence from it, and then project this down to the function class, as in you're trying to fit this value to the Q function approximator. But with CQL, because it uses this regularizer, you will find that this is not the update that happens when you use function approximators, but rather you end up projecting down still the value from your, you'll still project down the target value corresponding to an unmodified Bellman backup, but you'll have a separate offset that somewhat in a complex way entangles the learned policy pi theta, the behavior policy pi beta, and the Q function or the Q function features or the Q function gradients. So it's a bit more involved than projecting down a standard policy constraint value, as you see on the first equation here. Okay, so how does CQL perform in practice? So in practice, we first of all compute whether the learned policy value, that is the expected value of a policy under the conservative Q function learned by CQL, is actually a lower bound on the true value of the policy or not. We verify that first. So we do find that CQL does actually learn conservative Q values, and the Q values learned by CQL they are strictly a lower bound on the actual Q value. And this is not true for most of the other methods like BEAR, which are policy constraint methods, but they still sort of overestimate the learned policy value. On the ant-based task that we discussed previously in the policy constraint section, We do find that CQL can be quite efficient. For instance, here with respect to the baselines on imitation, naive off policy RL, policy constraint methods, as well as the approach 1 of which is inspired from KL control, CQL can outperform these methods by a non-trivial margin on these ant-maze tasks that we also discussed previously. And what this tells us is that CQL can do better stitching, because in these tasks, you do not have a single path that goes from a start location to a goal location, but you need to stitch together the relevant sub-trajectories to get that behavior. Okay, so far we have seen three classes of methods: policy constraint methods, model-based offline RL methods, and value regularization offline RL methods. In all these three methods, we followed a common theme, which is to make sure that for all unseen behavior, we penalize their value as much as possible. So either we prevent the policy from taking such actions which are unseen, or we make sure that the Q function or the reward value are small on those unseen outcomes. But what if we are in a scenario where, let's say, a Q function or a reward function can somehow generalize to unseen behavior, as in they can make the right predictions of the Q function or the reward function on those unseen state action pairs. In that case, turns out that, as expected, we would not want to be conservative, because just running naive off policy RL can actually give us a much better solution in such a scenario. But figuring out whether that is the case or not is a big question. So one of the promises that uncertainty-based offline RL methods give us is that they allow us to figure out when our Q function or model can generalize and when they can correctly generalize, and allow us to accurately use the fact that we can potentially solve the MDP without really requiring the need for any kind of conservative correction. So there's almost like a spectrum here, where on one end of the spectrum we have the methods that are naive off policy RL methods, which do not apply any conservatism. On the other end of the spectrum we have methods that do apply some conservatism. And uncertainty-based methods can help us figure out where is the right point on the spectrum that we should be for a particular problem. Now, just like any other class of RL methods, there are two ways to implement such methods. You can do a model-based approach, or you can take a model-free approach. I would argue that if we, along the model-based route, we already saw how to implement uncertainty-based offline model-based RL methods. Because the methods that we saw in the model-based land did actually take into account some sort of uncertainty metric, where this uncertainty was either defined as some sort of disagreement of the ensemble of dynamics models, etc. Now, there could be other choices of this function U which are potentially up for exploration, but these methods do actually fall into this uncertainty-based category. In the model-free land, one easy way of doing uncertainty-based offline RL is to just use this uncertainty function that you computed in the model-based land, for example, the function USA on this slide, and modify the reward function using it and run explicit model-free RL on it. However, something like this ends up being not much different from policy constraint methods, because typically modifying the reward function independently of each other on each state action pair ends up being sort of equally loose as applying a policy constraint on each state action pair independently. So in that case, this is not the most desirable thing to do. So then what can we do better? So one approach of doing better is to directly model some notion of Q function uncertainty and use that Q function uncertainty to guide how we should update our policy or how we should do policy improvement. To understand how we can use some notion of Q function uncertainty for policy improvement, let's define a sort of uncertainty set of Q functions given a data set. So this, the symbol P sub D of Q pi, what it denotes is, it denotes the set of all possible Q functions that could in principle be possible candidates for Q pi, where pi is a particular policy, given the dataset. So a dataset specifies certain transitions, and if my Q function satisfies the Bellman consistency equation with respect to the policy pi on those transitions, it is a potential valid candidate because it can be Q pi. Now, because we have not seen all possible state action pairs in the MDP, we cannot say exactly which of these is Q pi, but there is a set of possible candidates that are all valid. So let P sub D of Q pi denote this set. Now, I would argue that one easy way of doing uncertainty-based offline RL is to essentially update the policy using a slightly different form of policy improvement step, where we would now, as like a standard policy improvement update, we would update the policy according to the expected Q value, and the expectation here is also taken over all possible Q functions in the uncertainty set. But we'll also penalize the policy to be more conservative when there's more uncertainty. So if the uncertainty set of Q functions has like a high variation, we would want to make sure that the policy does not get updated too much in there, because we are not certain about which of these Q functions is actually the true Q function of the policy. So if we use some update like this, where the function unc of p sub d of q pi can be instantiated in many ways. For example, you can use the variance over the Q functions, etc. You can get an approach that does actually do uncertainty based offline RL. So given this framework, the next question, or the remaining piece to get a practical algorithm out of it, is how can we actually model uncertainty sets over Q functions? So one of the common ways of modeling the uncertainty set over Q functions is Bootstrap Ensembles. And Bootstrap Ensembles also apply to other methods. And in the Q function, or in Q-learning land, this is one of the more popular techniques of doing so. So in this case, what we'll do is we'll maintain an ensemble of Q functions. So let's say we have n Q functions parameterized by different parameters, Q phi 1 to Q phi n. What we'll do now is we'll do two things. First of all, we'll partition our data set into independent partitions, and that is the bootstrap part of things, where a statistical bootstrap asks us to train different elements of the ensemble on different parts of the data which are disjoint. So we'll do that. And because Q functions also require their own labels or they also generate their own labels, in that the target values are generated from the previous instances of a current Q function, which is the target network. What we'll do here is we'll make sure that each of the Q functions is trained with their own corresponding target network. So there's no mixing there's a clear segregation of values across different elements of the ensemble. So when we do this, when we train each Q function independently on the independent subset of the data and with independent targets, we can actually, in principle, recover an approximation to this uncertainty set P sub d of Q pi as basically being a Dirac delta distribution over each of these independent particles. So you can think of this P sub d of Q pi as almost like an average Dirac delta distribution over possible Q functions that you obtain. And with this formulation of P sub d of Q pi, you can essentially obtain essentially simplify the equation for the policy improvement step by basically replacing these expectations and uncertainties by sample means and sample variances. So you can do a sample mean over all Q functions and do like a sample variance over the predictions of each Q function, and that should be it. Now, it turns out that something like this, like just implementing this in practice, may suffer from an issue that basically happens in the following way. So you might end up finding that all of these Q functions in the ensemble, they'll have less uncertainty. They'll not be too diverse, meaning that you are training these Q functions, but the uncertainty represented by these Q functions might actually be an underestimate on the true uncertainty, which means you are ending up actually underestimating the uncertainty, which means you are prone to taking out of distribution actions, or you're prone to overestimating unseen behavior. And something like this may not end up working as a result of this. And this is what has been observed in practice so far, in that getting such a method to work does actually still require either a policy constraint or a conservatism constraint that we discussed for the other classes of methods. However, there's one work which devises an improved ensembling technique, and that technique is called random ensemble mixture, or REM, which is from this paper cited below on the slide. What they do here is that instead of having a separate Q function ensemble, as shown on the slide in the top right, what they do now is that they have an ensemble of Q functions, but they define their Q value as a random convex combination of the Q function predictions of these ensemble elements. So you have Q phi j's, you would sample a random convex combination, which is a vector of alphas from some distribution, and you will basically sum up the Q values of these different ensemble elements weighted by alpha j's to obtain the right Q value. And what they do here is they assume that the uncertainty function is 0. They don't even consider that. But just using this random this random ensemble or randomly mixed ensemble value of the Q function, they find that they can actually do quite well on data sets which have high coverage. So if you have high coverage over the state action space, a standard naive policy RL method, in this case it was a DQ network algorithm, did not perform so well. But the REM algorithm applied with DQN training did actually perform much better than that. And it also outperformed some other algorithms in this regime. But overall, a general solution for which is based on ensembling and uncertainty estimation for Q functions has been a bit hard to obtain. And by a general solution, I really mean that a solution that works across all kinds of dataset compositions, meaning that if your dataset is not high coverage, it has a very narrow coverage, the method should still be able to work well under that scenario. And that has been a bit hard to obtain in this setting. And they often have, or like uncertainty-based methods have often been combined with policy constraints or some kind of overestimation avoidance methods. And so, in a sense, it's unclear whether the real contribution is coming from uncertainty or not. To summarize, we covered 4 different classes of modern offline RL methods. We covered policy constraint methods, model-based offline RL methods, value-regularized offline RL methods, and uncertainty-based offline RL methods. Policy constraint methods often work well when the behavior policy distribution is easy to model, since they require a behavior policy estimate to express the policy constraint. But they also tend to be more conservative. Model-based offline RL methods often work quite well when the data distribution is relatively high coverage and it is easy to learn a model on this data up to a very good degree of accuracy. Value-regularized offline RL methods often tend to be less conservative and can also in principle be augmented with either dynamics models or policy constraints if you need it. In this table, I've tried to summarize some of these broad classes of methods along with what kinds of objects do they modify in the RL problem and what extra requirements do each of these classes of methods typically have. Please feel free to pause the video at this point to go over the table in more detail. In addition, I've listed a number of additional readings for this part of the tutorial. This list by no means is exhaustive and it mostly consists of papers that have recently come out in the last 2 years. For a more exhaustive list, please refer to the references in our summary and survey paper listed at the top of this slide. Okay, in this part of the tutorial, I'll talk about off-policy evaluation and model selection. So far our goal has been to find a good policy given access to a static offline dataset. But the goal in off-policy evaluation, or OPE, is to find the value of a given policy pi without running this policy in the environment. So given access to a static dataset D of interaction, we want to compute the value function of pi or the policy performance, the policy return, etc. So OPE can be used to perform comparison operations, such as we might prefer to use policy pi1 over policy pi2 if its estimated value function using OPE is better than that of pi2. In practice, this is used behind deciding which treatment plan to follow in a healthcare domain, as shown in this paper. So why do we need off-policy evaluation in offline RL? So OPE is a method to perform model selection, which means selecting hyperparameters, policies, or just statistical models in the offline RL problem setting. And why do we need model selection in offline RL in the first place? So similar to supervised learning methods, excessive training on the same offline dataset can sort of produce poor solutions in offline RL. And this is not just due to statistical overfitting, but due to many other reasons which are potentially also unknown. And it is also unclear how to select hyperparameters for any algorithm. And the reason why hyperparameter selection is very important is because offline RL methods can be extremely sensitive to hyperparameters, which can make the difference of the method working to the method not working at all. So now what we'll do is we'll cover some methods for off-policy evaluation in very brief. So the first class of methods are called direct methods. And they are called direct methods because they tend to directly estimate, let's say, the MDP that we are in, for example, by fitting a dynamics model and a reward model, or by computing the Q function of the policy and use that to compute the value function or the return estimate for the policy. So a model-based approach here, as I just said, you can fit a transition dynamics model and a reward function model and then compute the return of the policy under this model. A model-free approach here is fit at Q evaluation, where you would basically try to train a Q function to match the Bellman consistency equation for the chosen policy pi. And you can do that by just training a regular actor-critic style method without the actor, or without training the actor. And then basically compute the estimate of the return by taking the Q function, the expected Q function value of the initial state and the initial action drawn from the policy. Such an approach actually works quite well in practice for a lot of high-dimensional problems, as shown in one of the references on this slide. You can also have importance sampling-based OPE methods, where, as Sergey discussed previously, you can do per decision importance sampling. So you can take trajectories of experience from your dataset and reweight them to look a lot like the trajectories from the pi theta policy that we want to evaluate. So we are basically reweighting the entire return of the trajectory by the importance weight pi theta tau by pi beta tau. And this density ratio can then be broken down into per decision importance weights, or a product of per decision importance weights, where per decision importance weights are given by pi theta of AT given ST divided by pi beta of AT given ST. And by then computing this expectation empirically over the data set, you can obtain a return estimate. Now, such an important sampling method often suffers from high variance, and thus is not the most desirable method here. But you can also improve them. For example, you can use a stepwise importance sampling estimator, where rather than multiplying the return of the entire trajectory by the importance weight of the entire trajectory, you can multiply the reward of each state action pair by its corresponding importance weight until that time step. And something like this does improve over trajectory level weights, but certainly it's also not the most desirable thing because it also suffers from high variance. Moreover, these importance sampling methods do not really exploit the Markovian structure of the environment, meaning that the data comes from an MDP. So in principle, we could have trained like a Q function like quantity to maybe better exploit the structure in the data, or better exploit the Markovian structure, which is not taken care into account here. One way to improve importance sampling is doubly robust estimators, which is also what Sergey covered previously. And the goal here is that, let's say if you can come up with a different estimator for the return. So let's say you can come up with an estimator that is biased potentially. So it's like, let's say a Q function, but it still has low variance. Then what you can do is you can combine the importance sampling estimator and this other estimator to obtain an unbiased estimator, which has lower variance. So let's say you want to evaluate the value function of a policy in a bandit problem where it's just the expected value of the reward under actions drawn from the policy. And let's say you have a potentially biased estimator, which fits the reward function or fits a model to the reward function and computes the expected value under that. What you can do is you can take the importance sampling estimator and combine this with the separate biased estimator in a way that now this new doubly robust estimator still is unbiased in expectation, and it has a lower variance provided that the separate reward model is good enough, as in it's close enough to the original reward function. You can also do the same with the RL scenario, where now instead of this nice clean expression for the importance weighted quantity for the value function, you'll now have a recursive relation, and this was also covered previously in this tutorial. And what you can do now is you can convert this to a doubly robust variant, where instead of having the reward model, you will have a learned Q function, which can be learned using any other method like fitted Q evaluation. And these methods tend to be better than importance sampling methods, and there are many other variants of this which you should check out in the references. There's also a third class of importance sampling methods called marginalized importance sampling, which basically aim to move away from importance sampling over the trajectory distribution and exploit some Markovian structure to compute importance sampling over state distributions. So you want to, instead of computing the density ratio of the entire trajectory, you want to compute the density ratio of marginal state distributions under pi theta and pi beta. And then you can compute the return of the policy using just an empirical sum of the density ratios of the marginal state distributions multiplied by the reward. Now, one of the ways to do it is this method called dual dice, which has this key insight that the importance weights W of SA of the state action marginal density ratios are basically the solutions to this optimization problem, this quadratic optimization problem, which still has a d pi or state sampling from d pi in this expression. So what dual dice does is that it applies a change of variables so that the state distribution S in the second term, where S is sampled from d pi of S, ends up becoming state sampled from the initial state distribution. So if you look at the expression, the second term in the bottom part of in the bottom equation, you'll find that S naught is drawn from D naught. And the way to do that is to note that this x of SA term can be expressed as the difference, or as the error between a new variable nu of SA and the Bellman operator applied to nu of SA. So it's nu of SA minus a Bellman operator applied to nu of SA, and this allows them to do a telescoping cancellation, and so you don't have d pi anymore, you have d naught. And this resembles a lot like a Q function, in that the function nu here is a lot like a Q function corresponding to zero reward in this scenario, for instance. Okay, to summarize OPE and model selection methods, we discussed three classes of methods. Direct methods, which include methods like fitted Q evaluation, have been shown to work quite well, but they also potentially suffer from the issues pertaining to distribution shift, similar to policy optimization methods that we discussed in the previous section. Marginalized importance sampling methods typically enjoy good theoretical guarantees. However, they also tend to be a bit challenging to apply in practice, especially with when we have samples and when we apply function approximators, because they typically require solving saddle point problems, which can be a bit hard in these settings. And we also discussed importance sampling methods that typically suffer from high variance issues, but are also unbiased. But especially when applied in offline RL scenarios where you have considerable distributional shift, they may actually end up producing incorrect estimates or incorrect importance ratios, especially when the behavior policy is also estimated. If you're interested, please check out this paper from 2019 that forms an empirical comparison of a lot of these methods, including a much wider class of methods than what we talked about today, and discusses their trade-offs. Okay, now Sergey will talk about how we should be evaluating our offline RL methods.
All right, in the next portion of the tutorial, I'll talk a little bit about evaluation of offline RL methods, and also go into a little more detail about when we might expect our offline RL methods to work well or to work poorly. So when and why does offline RL work? I discussed this briefly back when I described the problem statement, but I'll go into it in a little more detail next. So I said before that offline RL can help if you want to find the good stuff in a data set that has good and bad behaviors. So maybe you have a variety of suboptimal behaviors, some of which happen to have done something right, and offline RL can discover that. It can help when you want to get generalization, when good behavior in one place may suggest good behavior in another place. And then I talked about this kind of stitching idea where parts of good behaviors can be recombined. So with the stitching, I gave this example where you have a maze task where you've seen paths between different pairs of points in the maze, and then you want to traverse the maze from the lower left corner to the upper right. And you can recombine the pieces of trajectories that you've seen to solve this. To go into a little more detail on this, the first point might at first seem a little bit obvious, and it might also seem like there are some straw man methods that can do that very well. So if you just want to find the good stuff in a data set, why not just behavior clone the best performing trajectories? This is not at all as trivial as it seems, particularly in stochastic settings. So if you have a stochastic environment, then figuring out which behaviors were good and which were merely lucky is far from trivial. And the ability of reinforcement learning algorithms to reason about the long-term consequences of their actions and to reason about credit assignment through things like value functions can be a major boon in these kinds of settings. So just taking the best action you've seen so far is not always the best strategy, and offline RL methods can do quite a bit better in these kinds of settings in principle. Generalization is also something not to be understated. So generalization could mean that you saw good, an action that was good for one state, and then you can figure out that action is still good in another very similar state. But since offline RL allows us to utilize very large and diverse data sets, generalization could mean something far grander, something more akin to the sort of generalization that we've seen in large-scale supervised learning methods in computer vision and NLP, for example. The stitching idea is also something that is, perhaps a little more sophisticated than meets the eye. So you could think of it in this, somewhat naive geometric way, as visualized by this maze. But let me tell you about a little bit of work that we've done recently that maybe takes this idea to its logical extreme. So here we have data for a robot to perform one task, which is to pick up a ball from an open drawer, and a large amount of prior data performing a variety of other tasks, some of which can serve as prerequisites for this ball task. So some of the tasks involve doing uninteresting things, but some actually involve things like opening the drawer, moving objects out of the way, and so on. And if you have this prior data, in principle you can put them together and you can figure out a kind of common sense. You can say, well, if the drawer is closed and I need to pick up the ball, I know that I need to first open the drawer and then pick up the ball, even if you've never seen those components together. So you've never seen a single trajectory that opens the drawer and picks up the ball, but you've seen those behaviors separately in isolation, and offline RL can put them together and perform an entire task. So this almost has sort of a flavor of common sense. For if we saw a robot that couldn't open the drawer to pick up the ball, we'd say, well, it kind of lacks common sense. The fact that it can figure it out suggests that it might possess some sort of common sense. Okay, so offline RL can work in principle in all of these settings, but how do we know if it's going to work? This is actually a major challenge in practical usage of offline RL algorithms. If we can't roll out the policy, how do we know that it will succeed? This is a large barrier to the practical use of offline RL methods, and there isn't really a great answer to that. One answer could be, let's try to develop offline RL algorithms that are reliable enough that we don't have to ask that question. Another answer could be, let's try to develop better off-policy evaluation methods, which we can use to validate our offline RL solutions before deploying them. But of course that has its own downsides, because then you have to somehow validate your off-policy evaluation method. So this is in general a major challenge, and there's no single great solution. So usually this means that when we evaluate offline RL methods, if we're developing a new algorithm, we probably still want to use some kind of simulator to generate rollouts to see if our method works before we go and deploy it on a real data set where we don't have that luxury. There's no great answer for hyperparameter tuning just yet, but it's an active area of research. So for more on that, you can check out some of the OPE papers that Avril mentioned. But at least for the foreseeable future, it seems like we will need to validate our offline RL algorithms on simulated settings where we can perform rollouts to make sure they're working well before we apply them to real-world data sets and have any confidence that they'll perform reasonable things. So, of course, this makes it very important to answer the question, how do we evaluate offline RL methods? So if we disregard for a minute the actual real-world deployment, how do we even know that our algorithm is good? A very simple answer might be, well, if you just want to test if your algorithm is working well, why don't you just run some online RL algorithm, get a bunch of data, and then use that data to test your offline RL algorithm? That at first seems like a very natural and easy approach to take, and this actually represents kind of a typical protocol in prior work. Train a behavior policy PyBeta with online RL, then either log the data that PyBeta sees over the course of training or log data from the final policy PyBeta, and use that as a data set for evaluating and testing your offline RL algorithm. I'm going to suggest that this is not a good way to validate offline RL methods, and we should probably not employ this protocol if we want to develop offline RL methods that are reliable. In the real world, data might come from a wide range of sources with all sorts of pathological statistical properties. For example, it might come from non-Markovian policies, perhaps data generated by humans or hand-engineered controllers. We have to be able to use data that's representative of real-world settings and also leaves plenty of room for improvement. So you, of course, don't want to use data from an optimal policy, because then perhaps the best you can do is match the behavior of that optimal policy. You want to use suboptimal data from realistic sources with realistic challenges. And you need to validate that your offline RL algorithm can learn policies that are much better than the behavior policy from which the data was provided. Otherwise, there's not really much use for them. So without testing these properties, we can't really trust that our algorithms are good, and that's why it's so important to select appropriate data sets and benchmark tasks. So we recently developed a set of benchmarks for offline RL. They are by no means perfect, and I'll mention some of the shortcomings, but they do take some steps towards rectifying these problems. So this appears in a benchmark suite called D4RL, which has already been used quite widely for offline RL research. And the idea that we wanted to study in these benchmarks is to make sure to hit on some of the important principles. For example, data from non-RL policies, including data from human users. So we included some data of humans teleoperating robots based on some work by Rajeswaran et al., for example. We wanted to incorporate data sets that leave room for this kind of stitching property that I mentioned before. So the maze example that I showed is actually from the D4RL dataset, and it includes simple 2D mazes as well as more complex mazes with a legged robot. So this is kind of a plot of some of the data seen in the maze to give you a sense for the density. And we wanted to also include some realistic tasks. So we included a data set of photorealistic image-based driving based on the Carla dataset produced by Intel. We added data from a previous paper by Abhishek Gupta and Carol Hausman of robotic manipulation with a Franka robotic arm in a kitchen environment. Here the data is collected via teleoperation. And data from a traffic control simulator from Professor Alex Byan's lab called Flow, which simulates how an autonomous vehicle can regulate the flow of traffic to prevent traffic jams. So we believe these tasks provide kind of a sampling of somewhat more realistic environments with some realistic properties. So the complete set of tasks includes the standard Mujoko locomotion tasks, mazes to study stitching, data from humans for dexterous manipulation, collected with a data glove, whole arm manipulation, traffic control, and first-person driving. All right. Now that said, D4RL doesn't capture all of the important properties we want to have, and those of you in the audience are thinking about applications or developing your own benchmarks. There are a number of additional properties that are very, very important to study in offline RL, which perhaps haven't gotten quite the attention that they deserved. One of them is stochasticity. Stochasticity is very common in real-world settings, economics, healthcare, education, and it's often absent in commonly used benchmarks. But I think it's also a property that has very high potential for impact from offline RL. Non-stationarity is another major one. Things change over time in the real world. I think it's also important to study risky dataset biases. So if your driving data has never shown a car crash, can you understand to avoid car crashes? Some of the methods that overall discussed can actually handle this in principle by avoiding out-of-distribution actions. But this is, I think, a very important property to test, and current benchmarks often don't put enough emphasis on this. And of course, partial observability. This was not discussed in detail in this tutorial, but it's very, very important in the real world.
Okay, for the final part of this tutorial, I'll briefly discuss some open problems and conclude our discussion of offline reinforcement learning. So one of the interesting open problems to explore is to devise methods that do not act so conservatively. In that, there's not really a need for being conservative if our learned Q functions or dynamics models can generalize. Now, in principle, uncertainty-aware methods can be used to trade off conservatism and generalization, as we discussed before. But in getting right and calibrated uncertainty estimates, especially those that are calibrated across time, has proven to be extremely challenging. So one of the interesting questions to answer here is to devise ways to measure and optimize uncertainty that is consistent with the sequential nature of RL problems. We might also want to answer the question if we can ever avoid conservatism, especially in an expected case scenario, which is kind of more indicative of the sort of problems we'll face in the real world. Another interesting problem to explore is the problem of hyperparameter tuning. Now we know that offline RL methods can be extremely sensitive to hyperparameters, and we really need to come up with a completely offline way of tuning these hyperparameters. Now so far, general purpose off-policy evaluation methods have been used for hyperparameter tuning. But can we instead do something different, and we come up with almost like a validation error sort of metric that can be directly kept track of during training, and we can use that to do things like early stopping, analogous to supervised learning? Or can we come up with an off-policy evaluation method that is not general purpose, but that is specific to the kind of offline RL method that is being used to optimize the policy, in that it can only evaluate a subset of policies which my offline RL method produces reliably and may not work well for other policies, and that's fine because we only need to evaluate those specific policies which my underlying offline RL method would produce. Often at times we also care about ranking policies, and this is evident from the kind of literature that evaluates OPE methods. So then do we really need to train an OPE method to actually model the value function of the policy return, or can we directly train it to actually optimize for this ranking metric that we care about? That's another way of formulating OPE and potentially interesting to explore. Finally, one other class of interesting open problems are problems related to function approximation. So in general, we want to leverage the good generalization properties of deep neural networks in offline RL. But then function approximation can have a drastic negative impact on the performance of offline RL methods in particular. And this happens because the function approximator has no access to collecting new data in the environment, and so it has to learn from the kind of data we provide it with. Now, most of the RL methods typically utilize some function approximator to train other function approximators. For example, Q-learning would do bootstrapping onto itself. A model-based method would use the model to train the policy, and this can potentially lead to bad stuff happening in there. And you can characterize this bad stuff into optimization issues and generalization issues, and perhaps even more categories, and which we don't even know so far because there's not been a lot of work analyzing these in practice. But potentially understanding what kind of issues exist here, and maybe trying to address them by using perhaps a subset of techniques from things like representation learning, understanding the learning dynamics of neural networks in offline RL, using techniques that can handle non-IIT data or perform causal inference, or maybe even imposing structures on the problem, such as imposing a hierarchical structure or solving the problem for a specific class of rewards could be potentially very interesting in offline RL scenarios. There's a lot more open questions that I haven't gone into here, and you can find them in the different references that we covered today. Finally, I would like to conclude by revisiting back the motivation we started off today with, in that one of the primary factors behind the success of modern machine learning methods has been the availability of large, diverse datasets and the ability to train highly expressive and complex deep neural network function approximators on these datasets. Offline RL methods essentially aim to do the same for the sequential decision-making setting by converting large, diverse datasets of behaviors into effective decision-making engines. Today, we covered a number of offline RL methods, as well as we saw that there's a lot of work to be done in terms of addressing the open problems in this field. If you're interested, please visit our tutorial website for a number of resources, as well as our offline RL survey paper. Thanks a lot for attending our tutorial today.